time. Now, the next thing will be, if you recall from the phase diagram formulas we did, we spoke about this, like the formulas of unit weight. When you talk about unit weight is mass or weight over volume. Yes, and I also want to highlight something. I told you that unit weight and density are they are the same. In certain questions, they might not be technically the same. They are the same and they are not the same simultaneously. Now, density has to do with mass over volume. Unit weight is weight over volume, weight per unit volume. There are some questions. There's a particular question I saw. Like, I think I'll forward it to the group. They gave us the density. We also needed the unit weight. But then that's why you kind of need to understand these things. Because if you really understand it, you'll be able to discern, oh, this is what this is what that is. Now, let me also say that the bulk unit weight, when you see questions like, did we do such a question last time? Can't remember if we did. When the question tells you, okay, this amount of this weight of soil was taken for this volume, just know you're talking that for that single sentence, it is the bulk unit weight they are talking about. That is everything that was observed. If I go outside now, then if I take this bottle and then I take sand, put it in it, right? Now, everything, the volume I'm using and the sand weight I'm using is for the bulk unit weight. That is by the way. So now if you have the unit weight of solids is what? Is also G. Remember, specific gravity of solids, and then the unit weight of water is this. So if you bring this here, you have should I say final? This is the one before the final, right? So the penultimate formula you have is this. Then from this, we have one more derivation. We have that this whole thing here is represented with what we call K. It's represented with what we call K. It's also an index, basically, it's a constant. I told you there are a lot of constants that are taken into consideration. There are a lot of constants that are taken into consideration. One of them is this. This is a constant. Even viscosity is a constant because it's water you're dealing with. And now, but then viscosity can change based on temperature. So based on temperature, at certain temperature, this is a constant. If you know, even this guy was based on temperature. Specific gravity based on temperature. Viscosity is also based on temperature. So at a certain or at a particular temperature, the diameter of a particle falling in a liquid is this. This is a constant where L is in centimeter. Please, also something. When you have this in millimeter, the final formula will be 30. Why? Because originally this is taken as seconds. This is taken as seconds. Then when you convert it to minutes, like 1/60, you do some almost everything here will change. This from this originally is like in centimeter. Then it goes here, it becomes millimeter. So multiply, divide. This is in seconds. It changes to minutes because you are considering it in centimeter per minute. Practically, you are doing the practical is in centimeter per minute. So this changes to minutes. This is in centimeter. This is a constant. This is a constant. This is a constant. But unit weight generally, according to what we did the last time, we said unit weight is in kilonewton per meter cube, right? Kilonewton per meter cube. Why? Because it's weight. Weight is in kilonewtons. So, but here we are taking it as gram per centimeter cube because that's what we are like. That's the practical. That's what we are working with. That's what we are doing this. And then you see we've got centimeter cubes. There are a lot of cube. And even cubes, there are too much cubes. Problems come. Begin to cancel. So that is why we didn't bother. Like you don't even need to bother changing it back to this. They just work with what they just did was This is given to us in millimeter. This is given to us in gram per centimeter cube. This is a constant. This is given to us in minutes. T is given to us in minutes, and then L is in centimeter. So when you do all this, this is what you should have. So you can note that before you come here. So that is why this changes from 18 to 30, because it's mainly because of this guy. Now, so L is in centimeter, T is in minutes. What else? All the other ones, they remain the same. Okay. Now, okay, let me give us a few seconds to put this. Okay. Yeah. It's in centimeter. At this point and at this point, it's in centimeter. Yeah. It's in seconds. The T here is in seconds. Then it was in. Okay. So from this point now we move on to 30. This 30. So the reason for this 30 is at this point, this is in centimeter. And then at this point, this is in centimeter. These ones, they were calculated in gram per centimeter cube. But these do not really affect. Number one thing that affects here is this L. L is in meter per second. We converted it to centimeter. The next thing is the main cause that changed the number. Normally, if you're dealing with centimeter and millimeters, like those kind of values, it should just be, you should have been something like maybe 0.18 or 18,000, values like that. But the reason it changed to 30 is because of this 60 here. We had a division of 1 over 60 because you are converting from seconds to minutes. So that's the reason why 30 came up. Eh? As I said, there are a lot of constants that are taken into consideration, and there are a lot of conversions, constant conversion. So at the end of the day, this is what you get, but we don't want to go deeply into that because we don't need it as far as this course is concerned. So, but then that's like a very, very brief explanation for it. Yep. Yeah. L. So L there, L, K. K is a constant. K is this is K. No, it's this one we took away, this guy. And K is at a particular temperature. K changes based on temperature. The same way this guy changes based on temperature. K also changes based on temperature. Okay. What's the full meaning of K? It's a constant. I can't recall the name. It's a constant that has to do with viscosity, some other things, but I do not remember the name. I think you can check it. Okay. Now, we move to plasticity of fine-grained materials. Plasticity of fine-grained materials. This is it the most important? Yes, it's the most important section here because all the calculation is part. This is where it will come out from. Plasticity. Well, normally this course is very, very, it's broad, right? And there are a lot of interwoven concepts. So I think one thing that is helping right now is all these things are given in chunks. Hmm? All these things are given in chunks. Even the lecturer, the notes he compiled, they are from different textbooks. So many, there's in different textbooks. And all this, it's some things from the lecturer slide, different. So you are just bringing different things together. It takes a whole lot of time. But then if you can review these things, I'm trying as much as possible to pick out the important concepts. If you can review these things properly, try to check the correlation with past questions and work out questions, you are actually going to be good. For question 1 and question 2, it always comes out in these two sections. This, by God's grace, finalizes everything on soil classification. Question 1 usually has something to do with the soil. It has something to do with this, the phase analysis. Well, this question 2, usually is a mix of theories of soil classification and then also telling us about, it's also talking about this plasticity. So now, the plasticity here, when you say we we've been doing CG, like stress strain CG, mechanics of materials. We did mechanics to this structural. So in this case, we should not be strangers when it comes to plasticity, because plasticity is basically, as you know, when you say material is elastic, it deforms, comes back to its original formation. When a substance is plastic, when it deforms, it doesn't come back. It will deform, but it will not come back, right? So that is plasticity. So soils tend to be plastic. Fine-grained soils tend to be plastic. They tend to exhibit plasticity. Okay, so fine-grained soils tend to exhibit plasticity, and then there are things we really need to know. This guy, Atterberg, he loved soil so much, did lots of experiments, and then he began to get different indexes, limits, and yes. You see questions like, they'll tell you about soil cohesion and the cohesionless soil. Now, this has to do with the cohesive soils. Cohesive soils are soils, that stick together, materials sticking together. So, when you look at cohesive soils, there are different states. Number one, cohesive soil exhibits plasticity. There are different states for cohesive soil. Number one, there is the plastic state. 2, there's liquid state. 3, there's shrinkage. Should I say shrinkage state? No, let me say shrinkage limit. Plastic limit, liquid limit, shrinkage limit. And for every one of them, they have their corresponding indices. We've got the plasticity index, liquidity index, shrinkage index. We've also got the consistency index. Now, what are these terms? The first term, the liquidity limit. Now, so what is this liquidity limit? The liquidity limit is the point at which the soil tends to not become liquid anymore, and then it becomes plastic. It is that point at which the soil no longer exhibits a liquid nature, and then it now begins to assume a plastic nature, right? So, and one thing you should also notice, for everything we are doing here, it's all in relation to the water content. Recall when we did soil phase diagram, we spoke about water content, we represented it with the small w, and then we have, yes. So everything we are doing here is in relation to that water content, because we are looking at the water. It's the content of water in these materials that gives us all these limits. Now, the liquidity limit is the value of the water content at which the soil, the fine-grained soil, please, this is only limited to fine-grained soils. It has nothing to do with coarse-grained soil, because you do not do hydrometer analysis for coarse-grained soil. What we do there is sieve analysis. Now, so the liquidity limit is the value of the water content at which the soil no longer exhibits liquid attributes and then transcends onto plastic attributes. Technically, it behaves as a plastic solid. It deforms. It doesn't go back to to it. Okay. So the liquidity limit, it is the value of water content at which the soil no longer exhibits liquid attributes. It's not liquid anymore. Basically, when you displace liquid, it moves. Like, it assumes the shape of and things like that. But then, at that point, it refuses to be liquid, and now it becomes plastic, becomes stubborn. You move it, it doesn't return. The value of water content at which soil no longer exhibits liquid attributes and now moves on to plastic attributes, becomes a plastic solid. In sense that, like I said, you move it, it doesn't return. The formation is now permanent, which is, in simple term, plasticity. So it is denoted by this sign, and like I said once again, Everything is in relation to this water content. Now, okay, then what is the plastic limit? The plastic limit is the point at which this soil now says, okay, it has been liquid, it has been plastic, it no longer wants to be plastic. Now, it becomes brittle. In terms that when you deform it, it breaks. So the soil now exhibits brittlity, like when materials can break, a material that can break, that is a brittle material. So the soil now, under any form of stress, if you apply stress, it breaks. It becomes a brittle material. That is the plastic limit. It is what? It is that point at which soil is no longer plastic and now it has attributes of being brittle in sense that it can break. Any pressure that is applied, it snaps. Okay. Now, then we have what we call the plasticity index. All these things, they can seem overwhelming, but yeah, I'll try to break them down in very simple terms. Okay. Now, plasticity index. The plasticity index is the range of formula. It's not formula. It's the range of values at which the soil is plastic. So it is the range of values for the water content at which the soil is plastic. That is the plasticity index. Now, why are we learning these things? Why do we need these things? We are learning them because, number one, you use them to determine the nature of the soil. We use them to classify soil. Everything here is under soil classification. We use them to classify soil. We use them to know, okay, is this soil, is this sandy? Is it gravel? Well, we are dealing with fine soil, so it can't be sandy or gravel. You'd ask, okay, is it silt? Is it clay? Is it an organic material? So that is why we are learning this, because we need it for the classifications. Do you have any questions so far? Okay. So plasticity index. It's represented with this IP. And then, like I said, it's the range of value in which the soil is plastic. And then you have IP as WL minus WP. So this is IP. Now, okay. So we've discussed liquidity limit, plasticity limit, plasticity index. Now we move on to the liquidity index. Now this liquidity index is sort of different. It compares, it is trying to know it is comparing the water content of the soil we are taking into consideration to the plastic limit. You're comparing the water content, the nature of the water content to the plastic limit. So this is the formula for liquidity limits represented with this IL, and then you have that is liquidity index. Now, okay, there's also the shrinkage limit. There's also shrinkage limit. Now, the shrinkage limit is, so the soil has been liquid, it has been solid, liquid, plastic, solid, brittle, solid, yeah. To the plasticity limit. So soil has been liquid, soil has been liquid, plastic, then solid. What else can it be now? So in the liquidity limit, at a point where the soil moves from liquidity, like from being a plastic liquid to being a solid, a brittle solid, there are some times that soil, doesn't want to get to that point. There is a range of values at which the soil becomes a semi-solid. And then as a semi-solid, it says shrinkage. How does shrinkage come there? Now, the water level reduces. it is decreasing in the water level. So that is why shrinkage comes up there. It is the point at which the soil is about to approach the plastic limit. Sorry, yeah, plastic limit, because it wants to become solid. But then at that point, before that point, the soil becomes a semi-solid for a while, begins to reduce in water content. Because for it to be brittle, for something to be brittle, most times it has to be like really dry. The inside has to be dry. Mm. So the water content reduces. It is semi-solid, so it's still solid, can still like fracture, but then there is still water inside it till it reduces that. Okay, till the point it gets what? Plastic. Till the point it gets brittle, can break. So that is the liquidity limit. So in short, liquidity limit is from liquid to plastic, plasticity limit from plastic to solid, the shrinkage limit. Now, before getting to this point, something happens for most soil. Before getting to that point, it needs to reduce water. So that point at which, okay, it has assumed the plasticity limit, but then it's not yet a full solid. It needs to reduce water. That is the shrinkage limit. Now, we have a now this does not have an exact formula. It doesn't have an exact formula. The definition. Okay. So the shrinkage limit is just, it is the point at which the soil has attained, this point before the soil has attained plasticity limit, but then it still has water content. So there is a decrease in volume. It shrinks. There's a decrease in volume gradually before it becomes brittle. So that is it. The point at which it attains plasticity. Just put in your own grammar, because that's what I'm doing. It attains plasticity limit, has already reached it, but it is not yet brittle. Like it's not yet, no, it's not yet brittle to break. Now, at that point, it reduces in the volume reduces. There's a decrease in volume gradually until it gets to the brittle nature. So that is the shrinkage limit. So however you want to put it, just put it down. I'm just trying to say these things don't. It's better you just don't try to cram them. Most of the time, they are, you can get the meaning from the words, put the formulas in, things like that. Those will help you remember the definitions and the formula. So now, okay, this. So So, this is the liquid limit. This is a graph. It's a graph to represent these points that we've been talking about. This is the liquid limit to the plastic limit. From liquid to plastic limit, basically, at this point is a liquid. This one is a plastic solid. Plastic solid, solid, and then brittle. So, this is a graph to represent all these things that we've been seeing. Now, we have the shrinkage index. We have the shrinkage index. So the shrinkage index is shrinkage index is WS minus WP. So it's the difference between the shrinkage limit and the plastic limit. The difference between the shrinkage limit and the plastic limit is the shrinkage index. So it's the range of values. It is the range of values between these points. Yes, very simply. It's the range of values between these points. Any value you have here, that is like your shrinkage index. So, okay. Um, Consistency index. Okay. So there's one thing I didn't mention about the liquidity index. For the liquidity index, the liquidity index equals 1. That means the water content is at liquidity limit. Yes. And then if the liquidity index equals 0, the water content is at plasticity limit. Now, the opposite of this liquidity index is the consistency index. So the consistency index, liquidity index is, okay, yeah, we said it's the relation between water content and the plasticity limit. So the consistency index now is like this. For the values of IP, it is W minus WL over I, yeah, IP. IP. This is IC divided by IP. Yeah? Which one? Yeah, yeah. Yes. So this is it. This is the consistency index. This is the formula. It is the relationship between the water content and the liquidity limit. This one is relationship between the natural water content and the plasticity limit. So the consistency index is the relationship between the water content and the liquidity limit. This one, so you can see they are like two sides of a sword. Because now, in this case, if IL is 1, your water content is at liquidity limit. But in this case, if IC is 1, your water content is plastic. Then if IC is 0, your water content is liquid. And then obviously the sum of both of them at any given point would be equal to 1. So if you are given, let's say you are given the if you have the liquidity index to be 0.7, and then we are told to get the consistency index. Now, all you need to do is just 1 minus 0.7, that's 0.3. So the consistency index is the difference. The consistency index and the liquidity index, when you sum them together, you have 1. That is unity. So I think that's that on that. Is there any other thing? Yeah, that's that on all these. Then moving forward, there are some practical work, and sometimes they would also ask you to tell us to say how these practicals were carried out. For example, you see a question like, okay, they'll tell you to say the different types of analysis you have. Like, okay, there's hydrometer analysis, a sieve analysis, and then explain the extensive or explain briefly, extensively, however, how it is carried out. Now, all these values that we got, they are arbitrary in the sense that because we are dealing with things that are very small, so it's not practical, right, to begin to analyze it. It is when you take it to the laboratory that is when you'll be able to know all these things, all these values that are said. They were that's where this man comes up again. This is his spelling of his name. This is where it comes up. He brought up all these arbitrary formulas. Yes, they were correct because technically they were practical in the sense, in the theoretical sense, it was practical. but physically it wasn't really practical. You had to go. There are other things you need to do in the laboratory. How do you get the liquidity index? How do you do these things? What do you do to get them? So then someone else came in. Well, we'll mention his name later. Now, that was his name is he came in and then he did um, practicals for like the different practicals for he did for liquidity, he did for plasticity, he also did for shrinkage, like for all of them, right? But then I would only speak on the liquid. Now for a liquid limit, how do we get it? For the liquid limit, how do we get it practically? Now, from the experiment that was carried out by Otto Casirandi, he he got what we call the flow index. He got what we call the flow index. So let me explain this formula. Let me explain this practical briefly. It's actually not hard. Now, it took fine soil, dry one, took it, put it inside sort of a cup, and then there was uh, there was an apparatus. There's an apparatus, has its own name and everything. The whole device is called the mechanical liquid limit device. Yeah, it's the standard mechanical liquid limit device. Now, you put it there, took that cup, put it there, then you put a groove between. Like, this is the soil, you put a groove right between. We did it. We did it. I wasn't there. So then he put a groove there. Then he kept on blowing. So he keep on blowing till he closes up. That is it. That is the practical he did to get these values. And what do we want to get from that whole experiment? We want to chart the flow curve. When we chart the flow curve, we have the flow index. It is the gradient of that flow curve. Now, the flow index is, so I think I said this previously in the semi-logarithmic value for sieve analysis. Yes. In sieve analysis, you have semi-logarithm graph. This one also, we're also going to plot it on a semi-logarithm graph. So this flow index is considering the water content of that soil to the number of blows you would have. Now, it is the difference. You're going to do it like multiple times. You're not just doing it once. You have to do it repeatedly. You might get different values. But because it's the gradient, you're taking just 2 points, 1 point, 1 point, plot your gradient stuff. Then you have this divided by log n2 over n1, where these are 2 points on the water content side, and this is on the number of blows. So basically, you're plotting this against this against this. So this gives us our flow index. Please note this formula. I don't think we'll be able to do practical questions on this one particularly. But what I'll make sure we do today, or try as much as possible that we do today, is we see the sedimentation. No, sieve analysis. Yes. We'll do a question. That's actually not too hard, because you'll be given the sieve size. Be given the sieve size either in number, like there's number 2 sieve, all those things. You'll be given the sieve size either in numbers, or you'll be given in millimeters. Be given in millimeters. But what you need is that millimeter, because even if you are given in number, they tell you this one was done with the number 2 sieve, number 3 this sieve, number that sieve. You need to know the millimeter, because that millimeter is that size you're going to plot on the graph. You're going to plot the percent final, that is what is left over at every time you sieve, against the sieve size. So now we've done the flow index. Basically, that formula, the blowing formula, is what? Is to get the liquidity index. It's important to get the liquidity index. What about when we want to get the plastic limit? Now, for the plastic limit, There's a whole other formula, there's a whole other experiment that is done. By the end of the day, after performing that experiment, what we want to get is the toughness index. The toughness index it is the plasticity index, the ratio of the plasticity index to this, the ratio of plasticity index to the flow index, right? So let's say